There is no question about it. The Huey Cobra is a different breed. Almost everyone who sees the ship for the first time is struck by its slim, clean aerodynamic lines. The first flight quickly confirms the impression of its deadly effectiveness. But in order to fully understand the factors that dictated this design, we must review the evolution of the whole Huey family. For the roots of the AH-1G lie back in 1955. It was that year that the first Huey helicopter flew. This was a utility helicopter designed for the frontline evacuation of casualties. It was wide enough to accommodate litters across the ship for ease of loading. It soon became apparent that the basic Huey design would serve far more missions than just medical evacuation. The family of Hueys we know today was quick to evolve. The XH-40, the UH-1A, B, and D. The UH-1D, with its squad carrying capability, has become the standard troop transport helicopter in Army air mobile operations in Vietnam. And to offer armed support to these troop-carrying helicopters, the UH-1B, and later designation of the C with the 540 rotor system, was adapted to the armed helicopter role. Although this new breed of weapon helicopters has proven itself indispensable, there has been a basic compromise in aircraft performance. The addition of various weapon kits substantially increase both drag and weight. This has created the paradox of escort aircraft, which have less speed and maneuverability than the troop and cargo carrying vehicles they are to support. The Army realized that the quickest way to achieve a meaningful improvement was to modify the Huey into an integrated weapons configuration. These then were the design parameters of the Huey Cobra: maximum utilization of operational Huey components, packaged in a shape that would provide the performance and mission effectiveness that combat required. So the Cobra took shape around combat-proven Huey components. The 540 rotor system with its simplified door hinge design, the Army's 1,400 shaft horsepower T-53L13 turbine engine, and a transmission and tail rotor system which is common to both C and D model Huey helicopters. Tandem seating gives the Cobra the advantages of improved performance due to a slim fuselage and increased combat effectiveness for the pilot, co-pilot gunner team by means of virtually unlimited visibility. In 1963, Bell verified the tactical advantages of tandem seating in their experimental Sioux Scout helicopter. The chin turret and the lift obtained from the wings were also evaluated during the flight test program of this concept aircraft. This prototype embodied the aerodynamic design which the Cobra reflects today. The Huey Cobra speed and maneuverability comes primarily from the greatly decreased aerodynamic drag. The fully armed Huey gunship, with a fuselage 108 inches wide, has a flat plate drag area of up to 35 square feet. The Huey Cobra, with equivalent armament, has less than 1/3 the drag of its predecessor. This reduction of drag, coupled with the increased horsepower, provides the Huey Cobra with increased airspeed and rate of climb. This will permit the Cobra to arrive in the target area sooner, remain there longer, and carry a greater ordnance load. For the first time, the troop-carrying helicopters of the Army will have an armed escort which can move easily in and around the formation, combining maneuverability with high forward speed for protection of the escorted ships. Closely linked to the Cobra's high-speed performance are the flight characteristics of stability and maneuverability. To utilize its high performance to best tactical advantage, new flight techniques have been developed around the Cobra's unprecedented maneuverability. These return-to-target maneuvers are the helicopter equivalent of fixed-wing acrobatics. When one talks performance, it is only natural to consider the rotor system. The Huey Cobra uses the standard 540 rotor, but the stabilizer bar is gone, replaced by a simple 3-axis electronic stability augmentation system. The SAS system is perhaps the key to stability during ordnance firing. These rate-sensing gyros are able to detect changes in aircraft attitude caused by wind gusts, rocket firing, or other external inputs. The SAS system is able to sense attitude changes and make control corrections before the movement is apparent to the pilot. This not only gives inherently better accuracy, but also allows both pilot and gunner to concentrate on the mission during critical firing passes. Armament is, of course, Huey Cobra's reason for existence. The aircraft has been designed with armament a functional part of the entire airframe. The TAT-102A chin turret houses a single 7.62 millimeter minigun. Other versions have dual weapon turrets with 2 40-millimeter grenade launchers, 2 miniguns, or 1 of each. The turret is attached to basic aircraft structure, just below the co-pilot gunner. Highly directed, flexible fire is possible from the turret through 230 degrees in azimuth, 50 degrees of depression, and 15 to 25 degrees in elevation. Placement of the gunner in front of the pilot offers him unequaled visibility. The gunner normally operates the turret. The pilot normally fires the wing stores. However, the gunner can control wing stores, and the pilot can fire the gun turret when it is in the stowed position firing forward. The forward station also incorporates sidearm flight controls, permitting the co-pilot gunner complete control of the aircraft should the pilot become a casualty. A fully articulated pantograph gun sight with built-in lead compensation is attached to the floor directly above the turret. This relationship of turret and sight minimizes gunnery errors due to parallax or deflection of intervening structure. The gunner has a choice of 1,300 or 4,000 rounds per minute firing rate. With a TAT-102A, the Cobra carries 8,000 rounds of 7.62 ammunition. Palletized ammunition is located in a bay directly behind the chin turret. Access to the ammo bay is provided on both sides of the ship. This affords extremely quick turnaround time, even with a mixed ordnance load. Huey Cobra wing stores are mounted on 4 hardpoints. These currently include the XM-18 minigun, the XM-157 2.75-inch folding fin aerial rocket pod with 7 rockets, or the XM-159, which contains 19 rockets. These wing stores can be mixed or used in pairs on the hardpoints, providing a maximum load of 76 rockets. A 20-millimeter installation is under consideration. Crew and aircraft protection has been designed as an integral part of the Cobra, not an afterthought. Pilot and gunner seats are protected by lightweight boron carbide armor panels. The pilot seat is built of steel armor. Critical engine components, the fuel control system, and the compressor section have also been protected by armor. The hydraulic boost system has been protected through redundant design. Self-sealing fuel tanks have the ability to seal 50 caliber penetrations in the bottom 1/3 of the tank. The middle third can resist 30 caliber penetrations. The top 1/3 is tear resistant. One of the strongest lessons to come out of Vietnam is the need for improved aircraft survivability. Let's consider infrared and the growing arsenal of lethal heat-seeking weapons. For the past decade, the aviation community has emphasized performance, only to realize that the ability to survive in a hostile environment must also be an important design consideration. The Cobra has been designed to meet the weapon threats of this decade. The AH-1G has been designed with a tailpipe recessed within the engine cowling. Air entering the sail provides engine compartment cooling and exhausts through and cools an IR heat shield, reducing the aircraft infrared signature. This IR suppression technique substantially decreases the probabilities of infrared-seeking missiles acquiring the Cobra as a target. The Huey Cobra retains the maintenance ease of the Huey family. No lubrication is required in the Teflon-bearing 540 door hinge rotor. Large hinged cowlings provide better than ever access to engine and dynamic systems. Avionics equipment is located in the aft fuselage. All antennas are buried or flush mounted to minimize drag. Most maintenance functions are similar to earlier model Hueys, and the Huey Cobra enjoys the same initial high time between overhaul as other Hueys. These design considerations were not arbitrary, but are the result of extensive constant feedback by Bell representatives in the battle areas of Vietnam. Prior to final design of the Cobra, top management of Bell went to Vietnam to learn from the men who fly Hueys what was needed in an armed assault helicopter. The needs defined by these men show up in the smallest detail of design. Take the emergency ordnance jettison system. The outboard loads are piston-driven downward with a force of 1,500 pounds. The inboard stores angled away from the ship with twice the force. It is a small item of hardware, yet it could make the critical difference in survivability in many marginal combat situations. And like all forms of insurance, high survivability design considerations buy a sense of security even should they never be used. It would be difficult to conceive of a more extensive test and evaluation program for any aircraft. The wide variety of ordnance has been extensively fired in situations which approximate ultimate combat deployment. The Cobra test program was flown by Army pilots with extensive Vietnam combat experience. The evolution of tactics for this unique helicopter represents the integration of the skills of these men with the expanded capability of this newest member of the Huey family. Currently, production Huey Cobras are rolling off the assembly line to join the battle in Vietnam. In the brief space of less than 2 years from the start of design effort, the aircraft entered combat. Today, the Huey Cobra, backed by a heritage of more than 3 million air hours chalked up by other members of the Huey family, is in the skies to ease the burden of the Army man on the ground.
I'm sure that it's apparent to everyone that your presence in this class says something about your ability. You're here because you have qualified to transition to the AH-1G. Every pilot wants to fly the newest aircraft. However, with the Huey Cobra, we have a far greater dimension. It is the Army's first helicopter designed specifically for the armed helicopter role. Many of you have been flying the armed UH-1B. You know it's done a good job. But you also understand better than anyone else their limitations. All the armament which was hung on the basic Huey cost plenty in speed and maneuverability. And it was to give greater capability in these areas that the AH-1G was designed. Let's look at the ship. The combat-proven components of the earlier Huey ships have been preserved in the Cobra. These include the 540 rotor system, the L-13 engine, the transmission, and the tail rotor drive system of the UH-1C and D. A Around these items has been wrapped a new aerodynamic shape with about 1/3 the drag of earlier Hueys with similar armament. The clean shape is a function of tandem seating. The pilot aft, the gunner co-pilot forward. The combination of increased horsepower gives the ship unique performance. Dive speeds of 190 knots, even with 2,000 pounds of ordnance. The ship is highly maneuverable, so you will undoubtedly find a whole new field of tactics evolve because of these near acrobatic return-to-target maneuvers. There is a wide variety of available ordnance, as this chart indicates. You can select any mix which will be right for your specific mission requirements. This varies from a lightly armed configuration with just the chin turret and perhaps 2 XM-157 rocket launchers on your wing stores, all the way to the hull configuration utilizing 4 XM-159 rocket launchers. I could talk a long time, and it wouldn't make as much sense as actually working with the Huey Cobra. So let's step outside and begin working with your new aircraft. The AH-1G pre-flight is not too different than the helicopters you have been flying, except, of course, that this is a gunship. And this should be your first check. Determine that the armament is safe and the battery switch off. Check your fuel level, a standard procedure. As you approach the engine compartment, you will verify that the air intake screen is clear of obstructions. In the engine area, there are 2 standard oil checks. This first, the oil level in the transmission illuminated by this button. Second, the engine oil level, which is located in the upper cowling area. Sump drain, again, a standard procedure that is a familiar habit. As you progress toward the tail, you will make the usual visual observation: condition and cleanliness of the wing and airframe surfaces, and the latching of all cowl and access panels. The tail has 2 gearbox oil levels to check: 42 degree and 90 degree. The oil level is easy to verify visually. Again, on this side of the ship, make certain the air intake screen is clear of obstructions. As you progress forward, the number 1 and number 2 system hydraulic oil checks should be performed. There are some checks in the co-pilot cockpit which would normally be done at this point for a single pilot operation. But let's complete our walk around before we move inside. At the nose, the usual checks. The cover has been removed from the pitot tube, and that it is open. Check the battery for condition and connection. And make sure the nose compartment door is secured. Let me stress, this pre-flight check has just touched on some of the specific items on the Cobra which are different. It should not be interpreted as being complete pre-flight, since that information is contained in the pilot's handbook. Once inside the cockpit, the co-pilot gunner should perform the following pre-flight checks. Adjust pedals as desired. Fasten safety belt and shoulder harness. See that the canopy jettison handles are secured and safetied. Governor emergency switch in auto. Engine air inlet switch in screen. The electrical power switch should be in the forward on position and be safetied. Instrument lights are off. Emergency collective, hydraulic off. The altimeter set and armament control panel switches set. Test the caution panel switch. Headset functioning should be checked. The gun sight should be stowed and secured, as well as any loose equipment such as the knife. The pre-flight from the pilot cockpit is, of course, more expensive, but basically the same as Huey helicopters you are already familiar with. Throttle is off. All lights and heater switches off. The engine air switch should be on screen. The force trim switch, forward or on. The hydraulic test switch, centered. Verify that the following are in the off position. RPM warning switch, emergency collective hydraulic, fuel, SAS power, master arm, battery, generator, and inverter. Compass slaving will, of course, be on mag. Non-essential bus, normal on. Now move the battery switch to on, unless using an APU. The inverter switch goes to main. Test your caution panel and master caution lights. Test the fuel gauge. Then place the fuel switch in the on position. Check the fuel pressure gauge. Check the engine idle stop release on the throttle and position the throttle just below flight idle. Decrease the governor RPM increase-decrease button for 10 seconds. You are now ready for engine starting. Once you have checked the rotor pads and have a fire guard in position, press the starting trigger. The L-13 engine starts slower and hotter than the L-11, and it may take as much as 40 seconds to reach 40% N1 when using the aircraft battery as a power source. Monitor the exhaust gas temperature. The maximum is 760 degrees centigrade. Release the starting trigger at 40% and advance the throttle to flight idle. Check engine and transmission oil pressures. Monitor the caution panel. Turn on all radios and SAS master and release the collective down lock. Prior to engine run-up, check the audio signal on the RPM warning switch. Then advance the throttle slowly to full open, 6,000 RPM. Takeoff should follow the normal practice. Whenever possible, lift off the ground about 3 feet. Hover briefly to determine that the engine and flight controls are operating normally. Then apply forward cyclic to accelerate smoothly into effective translational lift. Drop the nose slightly to achieve an airspeed of 60 knots. Stabilize airspeed and torque pressure as soon as a smooth rate of acceleration will permit. During a pilot's first takeoff in the AH-1G, he will probably think the helicopter is in an extreme nose-low attitude. Actually, there is very little difference in the takeoff attitude of this and the UH-1 type helicopters. The apparent difference is caused by the downward slope of the canopy rails on the Cobra. This nose-down illusion exists in all phases of flight, but the pilot will quickly adapt to this misleading apparent attitude. Most UH-1C pilots have by now heard of pitch cone coupling. This is the characteristic of the 540 rotor head to automatically reduce pitch under loading to keep RPM up. Under conditions of severe loading, the rotor RPM may overspeed above the red line unless the pilot adds collective pitch. This same condition is present in the AH-1G. since it also has a 540 rotor system. The increased airspeed of the aircraft makes the Huey Cobra even more susceptible. Briefly, the sequence of events starts when the rotor is subjected to high G forces, causing the blades to cone upward. As the hub bends, the pitch chain horns try to move but are restrained at one end by the control tubes. As the butt of the blade moves upward, trying to force the control end of the horn down, the pitch chain horn pushes the trailing edge of the blade up further, causing the rotor pitch to decrease. This then causes the rotor RPM to increase unless the washed out pitch is put back in by collective application. This rotor loading can occur in power on or power off flight, such as the flare in auto rotation. During maneuvering flight, the pilot should cultivate the habit of increasing collective pitch slightly when increasing G load with cyclic and decreasing collective when relieving the G load with cyclic. Up to an airspeed of 130 to 140 knots, the AH-1G is very similar, operation-wise, to the UH-1C. Above 140 knots, it is necessary that the pilot devote more attention to flying the aircraft and to planning maneuvers prior to doing them. As discussed earlier, the pilot should allow adequate altitude for pull-ups, adequate room for high-speed turns, and maintain RPM and torque control while maneuvering. And remember auto-rotation procedures and characteristics. To decrease airspeed from high speed down to approach speed requires quite a bit more time than most helicopter pilots are used to. During this time, the aircraft travels a considerable distance, and it is very easy to overshoot the landing area. As in the UH-1 helicopters, the AH-1G cannot develop enough rotor thrust to pull a high enough G load to cause airframe damage. However, the increased vibrations occurring can cause accelerated component wear. With increasing airspeeds, an increasingly larger portion of the rotor loses lift until the major portion of the available thrust is being used just for lift and forward speed, and only a small amount remains for use in changing direction. This is why there may be a mushing feeling to high-speed pullouts. A fighter pilot is well aware of somewhat the same effect in a fighter when pulling out of maximum airspeed dives. It is important that the Cobra pilot be very familiar with the altitude required for pullout at different airspeeds and gross weight. During high-speed dives, about 40 psi of torque seems to give the best feel to the aircraft. During a pullout, a lower collective angle gives a better response than pulling out with full power in. Also, using less than maximum available power gives a bit more margin for error in the correction for pitch cone coupling effects. It must be realized by the pilot that his helicopter is much faster than other helicopters and will be operated in more severe maneuvers. Pilot procedure errors that can be tolerated at low airspeed can be serious at high airspeed. So a complete familiarity with the operational procedures and characteristics of the AH-1G helicopter is essential. It should also be realized that operational limitations, such as maximum airspeed, are not to be exceeded. On older UH-1s, limitations could be exceeded for periods of time with only an increase in the rate of wear of the parts. Exceeding limitations under some conditions in the AH-1G can result in inadequate control response or abnormal flight attitude if the engine, SAS, or hydraulic system fails, or other possibly hazardous consequences. Auto-rotation is the most critical phase of handling any helicopter. Let's see how the Cobra handles. During high-speed flight, if the engine quits or the throttle is chopped, the aircraft pitches up slightly, causing the SAS to put in a nose-down correction. If the pilot takes no control action, the SAS drives the rotor down in front and then up and then down again, attempting to keep the aircraft level. This flapping of the rotor can be excessive and could conceivably cause damage to some of the rotating components or mounts. To prevent this flapping, the pilot should immediately apply a moderate amount of aft cyclic at the time of the engine cut. The pilot input will signal the SAS that the pilot wants a slight nose-up attitude and prevent the SAS from flapping the rotor down. The slight flare will also hold the rotor RPM up while the collective is reduced and the airspeed brought back to the 60 to 100 knot range. Throttle chop on the AH-1G at treetop level with high forward airspeed should be entered by flaring at once and decreasing the collective after the nose comes up. A hard flare can result in ballooning as high as 500 feet, so landing field selection can be made. Collective should be used to keep the rotor RPM within limits and the flare adjusted to control descent angle. As in all auto rotations with any helicopter, pilot technique must vary in accordance with the actual conditions of airspeed, altitude, and gross weight at the time of the engine failure. The nose-low illusion that exists in all phases of flight due to the downward slope of the canopy rails may disturb the transitioning pilot during his first autorotative landings. The normal tendency is to roll out of the flare to a nose-high attitude of 10 degrees or more. This, of course, results in initial ground contact with the heel of the skids. Landing in such a manner, especially if the ground speed is a bit too fast, will cause the helicopter to pitch forward abruptly after initial touchdown. Such aircraft pitching can damage the skid gear or dig the turret into the landing surface. It is necessary then for the student to force himself to push the nose beyond what looks like a level attitude just prior to touchdown until he learns what the true landing attitude is. After a few hours in each cockpit, the new pilot will adjust to this unusual appearing attitude, and it will be of no further concern. Although not as critical as in auto-rotative landings, normal landing visibility from the aft seat is somewhat restricted. When looking directly forward, the pilot finds that he can see little more than the gun sight and the back of his gunner's helmet. It is necessary then to develop the habit of looking forward to the sides of the canopy. Whenever possible, it is advantageous to perform circling or turning approaches to the intended landing area. Because of the necessity of looking through the sides of the canopy, many pilots crab the helicopter slightly to further improve their visibility. This crab should not be continued to the touchdown phase of the approach. At some point, shortly before touchdown, the pilot must look forward to see and correct for this crab. Now that you've actually flown the AH-1G, it's a little easier to talk about the aircraft. From the front seat, most pilots display the same tendencies. The cyclic stick is usually over-controlled due to its short length. Often, it is moved to the left when attempting to move it aft. This is caused by the natural articulation of the human arm. Many pilots fly the aircraft out of trim or bring the nose up in turns. The tendency to shoot approaches too fast is caused by the smooth aerodynamic qualities of the Huey Cobra. From the rear seat, we can anticipate many of the same problems, plus failure to adjust for the additional height of the rear seat, and the necessity to crab slightly during approaches for optimum visibility. In the AH-1G, we have a high-performance aircraft with no abnormal characteristics. Those of you with high-performance fixed-wing experience will find the transition into the Huey Cobra is much like coming home. However, those of you with only rotary wing experience or with relatively little flight experience will find that in-flight planning will be a little more demanding. During your first few hours of flight, you may encounter some difficulty in staying far enough ahead of the aircraft. You're all good pilots or you wouldn't be here, and the aircraft has already established an enviable record of safety and performance. These two factors combined will make the AH-1G the success that the Army expects it to be. Enjoy your flying.
the new ship you'll be working with, the AH-1G Huey Cobra attack helicopter. It is the first helicopter in aviation history to be designed as a weapons platform. It is very fast, can carry more than 1 ton of ordnance, and represents a significant increase in fire support for the Army's combat forces. The whole design was based on using many of the dynamic components of the UH-1 series helicopter and wrapping a new, clean, aerodynamic shape around them. It is this new fuselage which we should look at first, for it is a different breed of cat from the previous UH-1 models. On the earlier Hueys, all of the access panels and doors were made of thin aluminum skin. For all practical purposes, they did nothing more than cover the airframe structure. They could all be removed or opened at once, and the aircraft could be moved in this condition. The AH-1G is much more like a jet fighter. Many of the airframe panels are part of the structural integrity of the aircraft. They have aluminum or titanium faces with fiberglass honeycomb backs. They are designed to carry airframe loads and do it effectively. Let's look at the most extreme case. With the aft fuel tank access panel removed, the aircraft is in a marginal structural condition. Should someone try to move the ship by the tail, structural damage might occur. Obviously, to carry the loads which the structural panel does, a support such as a jack should be used under the tail section. As you go around the ship, you will find these structural panels everywhere. It may help you to understand why you have to remove 40 screws sometimes when you know that the panel could be held on with 6. Although the panel could be secured with so few, the aerodynamic flight loads couldn't be carried without using all 40. You'll also notice the screws themselves, flush Phillips head screws. They have been used because of the aerodynamic integrity of the AH-1G. They require a Phillips head screwdriver in most cases. The Army knows that there will be a lot of these to remove and replace, so there have been additional screwdrivers of the right size and type added to your tools for this ship. Components which produce unnecessary drag on the Huey Cobra have been eliminated. This design philosophy is apparent throughout the whole ship. Everything has been faired in or covered over. Take those rocket pods, for example. The shaped nose covers can make a difference of 11 knots in aircraft speed. But let's start walking around the ship and see where the main components which interest the airframe mechanic are located. The nose compartment door consists of a contoured laminated fiberglass panel with spring-loaded hinges and spring latch fasteners. A door on each side of the fuselage, immediately after the TAT-102 gun turret, gives access to the ammunition compartment. The cockpit canopy is 1/4 inch stretched acrylic plastic covering the entire cockpit area. The pilot's and gunner's door latches are flush mounted and located in the lower edges of each of the doors, which hinge upward and are held open by 3-position variable struts. When the jettison handles, located in the top of the canopy, are turned, the doors are separated from the canopy. 2 doors, one on each side of the fuselage, directly aft of the cockpit canopy, provide access to the hydraulic reservoirs. Construction is laminated fiberglass and honeycomb core. The engine and transmission are cowled on each side by doors which swing open fore and aft on articulated hinges. The pylon area is covered by a laminated fiberglass enclosure. Doors are provided in the center section for access to the swash plate and in the aft section for access to the engine oil tank. A 1-piece enclosure streamlines the engine tailpipe. 290 pounds of advanced type armor materials have been integrated within the airframe structure. to protect the crew and vital aircraft components. Crew seats are constructed of dual hardness steel with under and side panels of boron carbide. Engine, compressor section, and fuel control are protected by boron carbide panels. The pilot seat is a vertically adjustable one-piece bucket-type assembly mounted on two vertical tubes which hold it in place on the airframe structure. The gunner seat is a two-piece bucket-type assembly consisting of a back and bottom. The two parts are joined together and held in a fixed position when bolted in place directly to the airframe structure and is not adjustable. The tail boom is an aluminum alloy structure covered by aluminum skin. As in previous versions of the UH-1, a synchronized elevator is located on the tail boom. Doors and panels are provided at various locations on the tail boom to allow interior access for inspection and maintenance. The tail rotor shaft is enclosed by sheet metal covers on the tail boom and on the leading edge of the fin. They hinge open to the right and secure in the closed position with twist fasteners. The tail rotor drive shafts are the same as other Huey helicopters. The 42 and 90-degree gearboxes are also identical to the UH-1 series of aircraft. The tail rotor assembly is similar to the UH-1C, except for a design change in the shimming method for establishing trunnion centering. A completely new tail rotor hub is currently under evaluation and will probably be installed on later production AH-1Gs. Stub wings mounted on the fuselage are provided primarily as a mounting accommodation for external weapon stores. Each wing is attached to fuselage fittings with 5 bolts and has removable leading edge sections. The alighting gear consists of 2 skid tubes and 2 arched cross tubes of formed aluminum alloy. Fittings are provided on the skid tubes to accommodate ground handling wheels. To prevent abrasion and damage from contact with the ground, replaceable steel skid shoes cover the bottom side of the skid tubes. The AH-1G main rotor is 44 feet in diameter and has 2 27-inch cord blades on a 540 door hinge type hub. This system enables the Cobra to fly at high air speeds with exceptionally low vibration levels. The main rotor assembly is the same as the UH-1C. The pitch horns are different due to the fact that the stabilizer bar of the C model has been replaced by the SAS system. The mast is also not interchangeable, since it is heavier and has a series of different splines. Now that we have been around the ship, you will have noticed that a lot of components look similar to the UH-1 series of Hueys, while a lot of components look similar, but are stronger. The whole airframe structure is substantially beefed up, and individual items, such as a landing skid, are completely different. It is stronger and attaches entirely differently than UH-1 skids. The rotor blades are the principal source of lift for the helicopter. They are made from aluminum honeycomb and are bolted to the grips at the inboard end. The blades require careful inspection for nicks, scratches, dents, and voids. Your TM55-1520-221-20 has very specific descriptions as to what should be fixed and how to do it, and what should not be repaired but replaced. Like many other areas of the aircraft, this will be one of the most important parts of your job. Knowing the difference between what you can and should repair and what you should replace. Of course, all blades must be tracked after every installation. And this is a good time to go back to the Dash 20 and see the new type of troubleshooting table which has been provided. In clear, step-by-step procedures, the entire tracking operation is detailed. And after each step, there are choices to be made, depending upon how the test worked. The swash plate and support assembly is similar to the UH-1C, except the components are stronger. The swash plate uniball friction device and the collective sleeve collet are also similar to the UH-1C. The transmission is located directly ahead of the engine and is suspended by pylon isolating mounts on structural supports extending above the power plant deck. The unit is coupled to the engine through a short drive shaft. The transmission provides drive angle change and speed reduction through a train of spiral bevel gears and two-stage planetary gears to drive the main rotor mast. A freewheel clutch in the input quill coupling disengages to allow main rotor and gear train to turn freely when engine is stopped or is idling below rotor driving speed, such as in autorotational descent. The AH-1G uses the Huey Universal Transmission. It is the same basic transmission as used on the UH-1 helicopters, except that the AH-1G has no main generator. The starter generator is used as the main generator. A separate film in this series on the AH-1G covers the Huey Universal Transmission. It details where the quills, which are particular to individual aircraft, are located, and how these should be installed to adapt the basic universal transmission to any Huey helicopter. The complete engine and power transfer system is enclosed in an easily opened or quickly removable lightweight cowling. The turbine engine and its accessories are located after the transmission and are mounted on a platform deck to provide maximum accessibility for servicing and maintenance. The T-53L13 series gas turbine engine is a free turbine type, flat rated at 1100 shaft horsepower. Flat rating refers to the limitation on the engine due to the airframe. The engine itself is capable of 1400 shaft horsepower. The engine consists of the usual 5 sections: inlet, compressor, diffuser, combustor, and exhaust sections. The bipod and tripod engine mounts on the AH-1G are the same as on previous Huey helicopters. The tailpipe is surrounded by an ejector shroud that extends several inches past the end of the tailpipe. This ejector mixes cool air with the exhaust gases to reduce the infrared radiation. The open end of the tailpipe is directly above the tail boom and directed slightly upward so that a view of the hot end of the turbine is possible only from a position that is above and behind the helicopter. 2 similar but separate hydraulic systems are used to operate flight control power cylinders, stability augmentation system servo actuators, and the armament turret. Systems number 1 and number 2 are exactly alike as to their reservoirs, transmission-driven pumps, and module assemblies. If one system is disabled, the other system can still operate normally. In addition to operations for both systems, hydraulic system number 1 has the following special functions: tail rotor controls hydraulic cylinder, yaw stability augmentation system servo actuator, emergency collective hydraulic power provisions, and cyclic controls accumulator and lockout valve. Hydraulic system number 2 has the following special functions: armament system hydraulic power provisions, and pitch and roll stability augmentation system servo actuators. The electrical power systems consist of a DC and an AC system. The 28-volt direct current supply system is a single conductor system with a negative lead grounded to the helicopter structure. Alternating current is supplied by one 100-volt ampere single-phase inverter that converts the 28-volt DC to 115 volts AC to the SAS system, fuel quantity, gyro compass, attitude indicator, AC fail relay, and 26-volt transformer. The 26-volt AC transformer, in turn, supplies AC to the following: fuel pressure, engine oil pressure, transmission oil pressure, torque pressure, and heading indicator. The primary flight control systems are the main rotor collective, fore and aft cyclic and lateral cyclic, and the tail rotor controls. Each of these is a system of mechanical linkage, assisted by hydraulic servo cylinders connecting the pilot's and gunner's control sticks and pedals to those mechanisms which rotate with and directly control the main rotor and tail rotor. Obviously, the tandem seating configuration of the Huey Cobra will pose some complications in control rigging, since the system must be more complex than the side-by-side seating of earlier UH-1 aircraft. The AH-1G Stability Augmentation System is a three-axis stability and control augmentation system integrated into the conventional helicopter fore and aft, lateral, and directional flight controls. SAS provides a highly damped airframe during wind gusts and weapons recoil and was designed primarily to provide a stable weapons platform. One of the systems on the AH-1G, which is completely different from previous Huey models, is heating and ventilating. The crew compartments are ventilated by air drawn through a screen on the front of the pylon fairing and forced through the distribution system by a continuously operated transmission-driven blower. Air is distributed through adjustable ventilators on both instrument panels, vents to sides of canopy, and cushions of crew seats. Air leaves the compartments through a blower opening located in the aft bulkhead. Heat is provided by bleed air from the engine compressor system. Bleed air is also used through windshield nozzles for rain removal. Rain removal from the windshield is accomplished by setting the selector switch on the instrument panel to rain removal position. When the selector switch is in the rain removal position, no bleed air flows into the crew compartment. Armament is the Huey Cobra's reason for existence, and it has a great variety. Let's start at the chin turret. The TAT-102 armament subsystem is a hydraulically and electrically operated system providing wide angular coverage and rapid fire. The weapon is a 7.62 millimeter hydraulically powered automatic multi-barrel minigun. The weapon incorporates 6 barrels and 6 bolt assemblies which revolve about the longitudinal axis of the weapon. The weapon, with the delinking feeder, is mounted in the turret and is capable of short bursts or prolonged firing at rates of either 1,300 or 4,000 rounds per minute. The gunner's fire control panel is located in the co-pilot gunner station in the right deck, forward of the flight controls. The sighting station consists essentially of a simple compensating sight head and hand grip assembly attached to the aircraft floor by means of a 5 degrees of freedom support structure. The ammunition feed system consists basically of ammunition box assemblies, a crossover feed assembly, a flexible ammunition chute, and a synchronized cartridge drive assembly. The ammunition box assemblies are mounted in the aircraft aft of the turret assembly. The external stores pylon installed on the AH-1G equips the helicopters for carrying various external stores or weapons. The ejector rack of the pylon is equipped with an electrically operated ballistic emergency jettison device in each inboard and outboard ejector rack. The ejector racks must be cleaned at the end of each firing day in which the emergency jettison is used. The orifice in the outboard ejector rack must be replaced after each second jettison of stores. Installed in the AH-1G is the XM-20 smoke grenade dispenser, which releases standard smoke grenades used for spotting and identification. This dispenser is loaded with M8 or M18 smoke hand grenades by the armament crew prior to flight. It consists of 2 clusters of 6 canisters, either of which may be selected by the pilot. The wings each have 2 hardpoints for ordnance stores. Armament currently qualified for use includes the XM-157 launcher, which fires 7 2.75-inch folding fin aerial rockets. Also, the larger XM-159 launcher, which can fire 19 rockets of the same type. Both types of launchers are reusable. Inboard hardpoints on each wing can accommodate the XM-18 minigun pod. The gun fires 7.62 millimeter ammunition. Both the gun and the feed system are powered by a self-contained electrical system. The mix of weapons will change depending upon mission requirements, since the variety of armament available provides an extremely versatile attack capability. Your TM-20 contains complete requirements for special inspection, test flight inspection, overhaul and retirement, and the standards of serviceability for the AH-1G. There is flexibility in performance of these inspections to allow for the variety of climate and terrain in which the Huey Cobra will serve. The Army TNs, your -20 and -35 handbooks. Use them and be sure to add the periodic revisions to the books. Don't forget, the pilots of your unit depend on your skill and dedication.
That was just one of more than 300,000 practice power-off landings that'll be executed by Army pilots this year. For that one pilot, it was another chance to rehearse, under completely controlled conditions, emergency procedures that might save his life, his crew, and his aircraft, if he should ever lose his engine while in flight. I'm Lieutenant Colonel Bob Evans of USAVES, the United States Army Agency for Aviation Safety. Now, as pilots, we all know that there is a certain amount of risk involved in any power-off landing. But we can reduce that risk if all of us, pilots, command, and staff, know what we're doing. Department of Army policy says we'll conduct practice power-off landings and also lay out standard conditions and procedures that will be observed. So for the next few minutes, we're going to review not only what happens during auto rotation, but also the parameters of the training environment established by policy that must be satisfied before practice power-up landing can begin. The whole idea is to get us up to speed to handle an emergency that we hope will never happen, and do it safely. It's important to have a good understanding of what's happening physically during auto rotation, because these factors underlie everything that's required for maximum safety procedurally. Let's look at the situation in normal straight and level flight. Rotor motion generates a downflow through the main rotor disc. Lift overcomes the force of gravity, or weight. A forward component of rotor thrust provides a force to overcome helicopter drag. All forces are balanced, and the engine is producing the torque to maintain a constant rotor RPM. But what happens if now the engine fails? Engine power is no longer available to maintain rotor RPM. Downflow through the rotor decreases to the point it is replaced by an upflow due to the aircraft's descent. Looked at in another way, as a result of the engine failure, lift and thrust start to decrease. In addition to this, another factor is aggravating the situation. The radical change in relative wind produces a high angle of attack, and the resulting high drag slows the rotor, threatening to stall the blades unless corrective action is taken. The danger is that without immediate positive pilot action to change the angle of attack, rotor RPM will decay rapidly due to profile and induced drag. And because rotor lift varies as the square of the RPM, lift capability will be lost at a substantially higher rate. If this continues too long, rate of descent may exceed auto rotation capabilities for recovery. For example, a 10% reduction in RPM leads to a 20% reduction in rotor lift, a 1-to-2 ratio. For this reason, it is crucial to take all necessary steps as quickly as possible upon engine loss to ensure that rotor RPM is maintained. The obvious pilot action is an immediate down collective that promptly reduces pitch and angle of attack, and then to establish the required velocity of flow through the rotor that will ensure maintenance of rotor RPM. This can be achieved by descending vertically, but the rate of descent must be very high, in the several thousands of feet per minute, and obviously enough altitude must be available for this purpose. On the other hand, forward motion can be made to contribute a substantial share of the flow at a much reduced rate of descent. At zero or low air speeds, you can expect high rates of descent. The rate declines to some minimum point with an increase in airspeed, a flight condition you can choose by adjusting aircraft attitude in auto rotation. In many cases, minimum rate of descent is the preferred condition. By changing attitude to increase airspeed, rate of descent again climbs until a maximum range condition is achieved. Increases in air speeds beyond this point are no longer optimal and may even be dangerous due to progressive loss of lift. The standard procedures governing practice power-off landings in the Army are designed to produce a rate of descent that is a compromise between minimum descent and maximum range points. This also provides generous options for you to exercise in emergencies, allowing you to select any airspeed in the included spectrum for landing spot selection purposes without risking a hard landing. The allowable options translate into distance over the ground that, depending upon entry altitude, can be measured in the tens to hundreds of feet. If altitude remains the same, risk of hard landing, serious damage to the aircraft, personnel injury, or even death increases with either a decrease or increase in airspeed. Trying to stretch a glide by increasing airspeed beyond the maximum range rate of descent can lead to disaster, just as surely as decreasing airspeed below the minimum rate of descent. Looking at your options from overhead, range over the ground available to you from the initial entry point decreases if a turning maneuver is involved, due to the higher rate of descent that results from increased aircraft G-loading, even while RPM is maintained. Again, some degree of choice between minimum rate of descent and maximum range is available, but attempting airspeeds and rates of descent above and below the optimum band again can lead to serious consequences. All right, those are some of the concepts that apply to auto rotation. But in the execution of the power-off landing, there are many additional factors involved. So let's consider it in more detail. The landing maneuver must be conducted in phases, each of which has a specific purpose related to controlling rate of descent or airspeed, or both. The line of flight from entry to touchdown is therefore rarely a straight line, except at descent angles close to vertical where forward ground speeds are low. Achieving proper flight conditions that will set up auto rotation is of critical importance at entry. The objective is not only to down collective to reduce drag on the rotor, but also to counter loss of engine torque by adding right pedal, and then to select an attitude that will produce the proper airspeed and thereby the proper rotor RPM. This will place RPM in mid-green. You might call the initial part of power-off landing the steady state phase. This serves two main purposes. You adjust the controls to maintain rotor RPM and consequently preserve a suitable degree of lift so that descent to a lower altitude can be achieved safely, and also to conserve the kinetic energy available in the rotating mass of the rotor for application during later phases of the maneuver. At about 100 feet above ground level, a new phase begins, deceleration. The objective here is to decelerate forward motion and increase rotor inertia and RPM. Deceleration involves a substantial change in attitude, placing the rotor nearly normal to the flow into the rotor. As it is exposed to the full flow of the airstream, the effect is to accelerate the rotor. But this increase in RPM is at the expense of airspeed, a deliberate trade-off for during deceleration, the rotor is also building up both lift and kinetic energy due to that increased RPM. And both of these must be present if the next phase, at about 10 to 15 feet, is to succeed. During the entire autorotation to this point, collective has been pulled down. But now, an initial pitch pull puts a portion of that increased lift to work. During the initial pitch pull phase, that rotor energy that was built up is drawn on to sharply reduce rate of descent, and this affects both attitude and airspeed. By continuing to pull collective, you expend that high kinetic energy level built up in the rotor during deceleration, and which forces the rotor to continue its rotation during the landing phase, even though airspeed due to forward motion is lacking. The amount of kinetic energy stored in the rotor system is related to its mass and the effects of inertia. Low mass, low inertia rotors give up their energy quite rapidly. High mass, high inertia rotors persist in their rotation for longer periods of time. The effect is to cushion the landing, using the available lift to control descent, touchdown, and to hold the aircraft weight off of the landing gear during runout, if any. Only after aircraft motion is stopped do you down the collective fully to conclude the landing. That was a good standard practice autorotation. Each phase was carried out just about right on the mark. Now be advised that the penalty for failing to observe the successive requirements for each phase of a power-off landing can be pretty drastic. You can bend or ball up an aircraft without too much trouble. Test pilots have placed themselves at considerable risk in engineering test flights to locate the autorotative limits of each helicopter in the Army inventory. Sometimes the only way to find out where the limit is to step over it, like this pilot did. Fortunately, this time he walked away from it. Operating in the caution or danger areas of the high-velocity diagram, in this case low airspeed and insufficient altitude for autorotative recovery, can lead to hard landings. There's no denying the potential risks in power-off landings. But aviation safety organizations such as USAVES, together with various aviation center departments, have helped to define rational and procedural constraints that could lead to the execution of practice power-off landings with reasonable safety. It's these constraints that underlie Department of the Army policy with respect to helicopter power-off landings. The controlling idea is that power-off landing is strictly an emergency procedure. It should never be indulged in just for kicks or casually in uncontrolled circumstances. Accordingly, Army policy requires us to conform to specified criteria before we enter flight training for power-off landings. And it also requires that this training be conducted according to standard procedures that have safeguards structured into them. Army policy says that practice touchdown autorotations are to be conducted only during formal instruction at the Aviation Center, during rotary wing transition flight training courses approved by appropriate authority, during standardization evaluation flights, and when deemed necessary by the appropriate commander. Policy clearly requires that practice touchdown autorotations are to be controlled by the local standardization board as an organized and closely supervised program. Survivability during what is training for an emergency goes up in direct proportion to the extent which those policy criteria are applied. Afternoon. There's little doubt that for the instructor or standardization pilot, practice touchdown autorotations can cause pressure. For this reason, Army policy says that consecutive one-hour autorotation instruction periods should not be scheduled in any one day. Further, no more than 6 practice touchdown autorotations per instructor, pilot, or student are to be performed during any one instructional period. Policy also requires that training be conducted at a location that provides for a crash truck with crew standing by, air-ground communications, and a means for opening and closing the practice area. For night practice, specific training locations must be designated and equipped, and all minimum criteria must be observed. Policy also states that practice touchdown auto rotations may be carried out only in dual control equipped aircraft, with a qualified instructor pilot and one set of controls who is current and proficient in practice touchdown auto rotations in the mission, design, and series aircraft being flown. Only the minimum required flight crew is to be on board the aircraft during practice touchdown auto rotation.
Clear! Clear!
Inasmuch as each aircraft has its own auto rotation characteristics, all entry speeds and altitudes during the maneuver are to be as specified in the flight training publication for the aircraft that is being flown. The flight parameters used in these publications have been selected to present the student pilot with a set of conditions which, if followed, will offer maximum potential for safe execution of the auto rotation maneuver under the monitoring and control of the instructor pilot. Policy expressly forbids unanticipated surprise practice touchdown auto rotation maneuvers, so the student can concentrate on acquiring the necessary knowledge and skills for this vital emergency procedure, free of that particular pressure. The standard practice touchdown auto rotation then starts from an altitude of about 700 feet above ground level, or as directed.
Okay, lined up on final.
Collective pull down, throttle to flight idle, cyclic and pedals adjusted for coordinated flight. The steady state phase. Minimum descent airspeed. Maintained steadily, normally, without variation. Maintaining constant ground track. RPM holding steady. Approaching the next phase. The deceleration phase. Nose up slightly. Rotor nearing normal to the flow. RPM increasing, but held below 339 RPM by small collective adjustments. Airspeed decreasing in the expected trade-off of RPM for airspeed, expending rotor inertia for lift. Cushioning the descent to the ground with very little forward airspeed.
You've got all those points straightened out now that we've been talking about, especially that bit about reducing the collective to break the ground run.
The problem in doing that, of course, would be that the rotors might flex and cause aircraft damage. The whole idea is to use collective to keep the aircraft light on the skids until run-out is completed to protect the landing gear. Elements of the standard touchdown auto rotation we've just seen are applicable also to field maneuvers, starting from different initial conditions, at low level, say. So long as the highest obstacle is cleared by 50 feet, Army policy says the low-level touchdown auto rotation can be performed at designated training locations, provided approach zones are sufficiently clear of obstructions to permit visual contact with the point of intended landing from auto rotation entry to termination. That entry speeds and altitudes are as specified in flight publications for the aircraft being flown. That auto rotations will be straight in, maintaining a constant ground track, and that speed reduction climbs or pop-ups will not be performed. As a practical matter, entry to auto rotation may occur almost simultaneously with the deceleration phase, if entry altitude is near 100 feet AGL. And from then on, the maneuver is identical with the standard touchdown auto rotation from higher altitudes. A standard touchdown auto rotation with a turn differs mainly in the initial conditions. And as pilots, you'll need to pay some attention to what's happening to the aircraft during the turns that precede entry into auto rotation. We're watching a maneuver that includes a 180-degree turn. But you're not limited to this, provided other requirements are met. That you be straight in not less than 200 feet AGL, for example. If you'll remember, a while back we said that even if RPM is maintained, you'll experience a higher rate of descent during a turn due to increased G-loading. Because of this effect, you'll have to initiate the maneuver at sufficient altitude and be sure to maintain coordinated flight to be in a steady state condition by that 200-foot AGL mark. Auto-rotation then follows the pattern we've already described. Incidentally, while the flight training guides and other publications may call for minimum ground runs as the preferred termination, you shouldn't construe this as requiring precision touchdown or zero ground run auto-rotations. The policy with respect to forced landing exercises is straightforward. The Army encourages you to practice these maneuvers, provided they are conducted only to an approved training area. But descent must be terminated and power recovery executed at no less than 200 feet above the highest obstacle. Practice hovering auto-rotations are excluded from the minimum criteria we've been talking about. Except for instructor pilot training, policy says further that unanticipated surprise practice auto-rotations from hovering are to be eliminated.
The tactic here, remember, is to hold what you've got, because the situation could be critical. Rotor energy has not been built up. Increased pitch could slow the rotor down abruptly, causing immediate loss of lift and a hard touchdown. Hold the collective pitch setting, allowing RPM and lift to decrease slowly, cushioning the landing with remaining rotor energy as in the case of the standard auto-rotation by pulling collective slowly.
Of course, we've been talking about criteria and procedures in the training environment, and we haven't said a thing about what may be the most critical issue of all, surprise, and the crucial delay in pilot response it may cause. An engine can go at any time, under any operational condition, perhaps under something as straightforward as this mission involving 2 aircraft. When you're in flight, survival may depend on split-second reaction and coordination. There won't be time for extended discussion about who's going to do what. All that has to be worked out in detail ahead of time, with a clear definition of which pilot will perform which duties, planned and accepted at the outset. Sort out individual responsibilities, pinpoint possible landing sites, do everything possible beforehand to cancel out the effects of surprise. Confusion in the cockpit can kill you, but not if you've thought the problem through and have trained yourself to deal with the unexpected, quickly, proficiently, effectively.
I'm having a pressure problem. Someone had to take it down.
That instinctive reaction, automatic, precise. Collective full down, adjust cyclic for 80 knot attitude, adjust right pedal to counter loss of torque. May have saved them, for the pilot is ready for auto-rotation entry if need be. A number of lives and an expensive aircraft, saved by prompt and knowledgeable response to an emergency that could have had disastrous consequences. Department of the Army policy accepts the conclusion that, as a minimum, current policies and procedures have been effective in Army aviation accident prevention efforts. My business is aviation safety. And a safe power-off landing like this one is the payoff for me. And it can be for you and everybody else who flies in Army aviation when your training for power-off landings takes the safe approach.
anti-torque failure is a serious hazard to all aviators who fly single-rotor helicopters. Statistics compiled by the U.S. Army Board for Aviation Accident Research show that in the 53-month period ending 31 May 1971, there were 927 anti-torque malfunctions. The results of these malfunctions were a dollar loss of $39,699,000. 303 people were injured in the accidents that followed the malfunctions, and 109 people lost their lives as a direct result of these anti-torque malfunctions. Many of these statistics could have been reduced if proper corrective action had been immediately initiated. In single-rotor helicopters, there are many types of malfunctions which could lead to anti-torque failure. These malfunctions can be broken down into three main categories. The first of these categories is the loss of one or more of the anti-torque components. In this situation, some part of the anti-torque system physically separates and leaves the aircraft. This would include tail rotor blade separation and gearbox separation. The first indication of the loss of a tail rotor component will probably be a vibration in the aircraft and or a loud noise. In most cases, the nose of the aircraft will pitch down and yaw right after loss of the component. When forward flight is attempted, the aircraft will tend to roll left. The second category is a failure in the tail rotor drive system. This could be a tail rotor drive shaft failure or a transmission failure. With either of these failures, the tail rotor would lose drive and stop turning. Loss of tail rotor drive will most likely result in the nose of the aircraft yawing to the right, and if in forward flight, the aircraft will roll to the left along its longitudinal axis. The third category of anti-torque failure is loss of tail rotor control. This situation involves the inability to control the pitch of the tail rotor. This could be the result of a broken control cable or a pitch control link or a malfunctioning tail rotor servo. This condition will affect both the yaw and roll attitude of the aircraft, but the direction and severity of the aircraft reaction will depend upon the relationship of the tail rotor setting and the engine power setting at the time of the malfunction. If the malfunction occurs during takeoff and climb out, when the pilot has a high power setting and is using left pedal to correct for torque, the nose of the aircraft will yaw left when power is reduced. If the malfunction occurs during a low power setting, such as in a descent, the nose of the aircraft will yaw right when power is added. When an anti-torque malfunction is encountered in flight, several things should be kept in mind. The first consideration is that the anti-torque failure may not be immediately recognizable. The initial indications, such as noise, vibration, yaw, pitch, and roll, are also associated with an engine failure, a hydraulic malfunction, or main rotor control or component malfunction. However, upon encountering any of these indications, it is important not to allow the aircraft to lose forward airspeed until a more complete analysis of the failure has been made. Secondly, most cases of anti-torque failure do not result in complete loss of aircraft control unless the pilot fails to initiate and follow a determined course of corrective action. An attempt to control the aircraft should be made using all flight controls until it is determined which controls are affecting the aircraft. Cyclic control, applied opposite the direction of turn, will aid in maintaining flight along a desired course. However, the aircraft may be in an extreme attitude in regards to yaw and roll. Do not make rapid control movements, but don't be afraid to make large control movements, even to the point of contacting the control stops. If full movement of the cyclic control does not stop the yawing movement, then begin a slow reduction in power by slightly lowering the collective pitch control. Continue reducing power until the aircraft is under control. If the yawing movement is not correctable by the initial power reduction, auto rotation will be entered. Auto rotation should not be entered unless the aircraft is otherwise uncontrollable. The auto rotation should be the result of continuing the reduction of pitch and then throttle, and not a deliberate action. If auto rotation becomes necessary, the procedures for normal auto rotation should be followed to include termination of the maneuver. When the aircraft is under control and powered flight is being maintained, the next consideration is an important one. Even though the aircraft is under control and powered flight is being maintained, additional stress is being imposed on the aircraft's fuselage and tail boom. As flight continues, further disintegration of components may be experienced. Therefore, plans should be made to land at a suitable landing area as soon as practical. If possible, select a landing area large and smooth enough to permit a running landing. If wind is a factor, an attempt should be made to land with a crosswind opposite the direction of yaw. For instance, if the nose of the aircraft is yawed right, try to land with a left crosswind. There are three different situations that could be encountered in an attempt to terminate flight after experiencing an anti-torque failure. These situations are determined by the yaw attitude of the aircraft on final approach. In the first situation, the nose of the aircraft has yawed to the left after an anti-torque failure. After choosing a suitable landing area and prior to final approach, in turbine-powered aircraft, adjust the throttle to gain manual control. On final approach, slowly adjust the throttle to minimum operating RPM for the aircraft. When landing is assured, begin a slow deceleration to arrive at the touchdown point at a speed commensurate with the terrain of the landing area. As the aircraft nears touchdown, increase collective pitch to cushion the landing. The increase in torque will start correcting the left yaw by swinging the nose of the aircraft back to the right. If, after application of collective, the aircraft is still yawed to the left, increase the throttle to further align the aircraft with the direction of movement and complete the approach to touchdown. If the yaw condition cannot be corrected by application of throttle and collective, all forward motion should be stopped prior to touchdown. In the second situation, the nose of the aircraft has yawed to the right after an anti-torque failure. After choosing a suitable landing area and prior to final approach, in turbine-powered aircraft, adjust the throttle to gain manual control. On final approach, slowly adjust the throttle to full allowable engine RPM for the aircraft. When landing is assured, begin a slow deceleration to arrive at the touchdown point at a speed commensurate with the terrain of the landing area. If terrain features permit, plan to execute a running landing. As the aircraft nears touchdown, reduce the throttle enough to cause the aircraft nose to swing back to the left. As the aircraft aligns with the direction of aircraft movement, increase collective pitch to cushion the landing and touch down with a running landing. During the run-out, directional control is maintained by increasing and decreasing throttle. In the third situation, the aircraft is maintaining straight flight after an anti-torque failure. After choosing a suitable landing area and prior to final approach, in turbine-powered aircraft, adjust the throttle to gain manual control. When landing is assured, begin a slow deceleration to arrive at the touchdown point at a speed commensurate with the terrain of the landing area. If terrain features permit, plan to execute a running landing. As the aircraft nears touchdown, use the throttle to maintain the alignment of the aircraft with the direction of movement and execute a normal running landing. During the run-out, directional control is maintained by increasing and decreasing throttle. If directional control is lost at a hover or on takeoff or landing below 10 feet altitude, close the throttle, then execute a hovering auto rotation. If directional control is lost at a hover above 10 feet, close the throttle, reduce collective pitch, and attempt to level the aircraft. As the aircraft nears the ground, increase collective pitch to cushion the touchdown. There are many different things that affect the operation of anti-torque systems. When encountering an anti-torque malfunction in flight, the first consideration should be an attempt to control the aircraft and maintain powered flight. Auto rotation should not be entered as a deliberate action, but should be the result of continuing to reduce power in an attempt to maintain control of the aircraft. Anti-torque failure seldom results in complete loss of aircraft control, but the pilot must plan and initiate a course of action to maintain control of the aircraft. There is one case on record with the U.S. Army Board for Aviation Accident Research where an Army pilot successfully landed a UH-1 after loss of all but 18 inches of the entire tail boom. His determination to control the aircraft enabled him to land the aircraft and save himself and his crew.
The height velocity curve currently incorporated in the OH-58A handbook was developed by the Federal Aeronautics Administration using pertinent FAA regulations and procedures. The criteria utilized in the development of this curve were based on satisfactorily accomplishing touchdowns on paved surfaces with a sink rate within the design yield limits of the skid gear and accepting whatever the resultant ground roll. Since these criteria differ greatly from the Army philosophy, it was deemed necessary to develop a height velocity curve using the Army philosophy. To accomplish this, the United States Army Aviation Systems Test Activity at Edwards Air Force Base, California, was given the task. The purpose of this presentation is to introduce you to and acquaint you with the flight test technique utilized during height velocity testing. The information presented is an attempt to help you better understand the height velocity curve itself and how the data is obtained from its construction. Being exposed to this information should in no way tend to cause the formulation of the idea that you can go out and practice these maneuvers. Let it be understood that this is not a practice maneuver and should be considered in an emergency situation only. First of all, presented here is a typical height velocity curve. For the purpose of this presentation, we divided the curve into 3 segments. Area 1, high altitude, low airspeed. Area 2, knee area. And Area 3, low altitude, low airspeed. The reason for this breakdown is for simplicity and to point out the difference in technique used in these areas during the flight test. In all 3 areas, movement of the cyclic and collective controls was delayed for 2 seconds following throttle chop. This was done to simulate normal pilot reaction time during actual engine failure conditions. As you will see in the test footage, rotor RPM decay is very rapid, and in all cases, the RPM fell below the minimum power-off operating limits. In Area 1, at a height between 600 feet to 200 feet actual ground level, beginning with a high hover point, the curve was approached with conservatism. Starting with a pre-calculated safe altitude, a series of auto rotations was made, decreasing altitude on each successive maneuver until the actual curve point was reached. As may be seen, in this area, the aircraft was rapidly pitched nose down to an attitude of approximately 30 degrees, following the 2-second delay to regain rotor RPM and accelerate to the desired flare airspeed, or slot position, 60 knots to 100 feet. The technique was held constant throughout Area 1 over a spread of entry airspeeds. Let's again view the Area 1 test footage. RPM is below minimum. The nose is pitched down to an attitude of approximately 30 degrees after the 2-second delay to regain rotor RPM, and then accelerate to the desired flare airspeed. Now let's discuss Area 2, which is 200 feet to 75 feet actual ground level. In Area 2, there is less margin for error, and the technique for developing the curve was slightly altered. In this area, to minimize the probability of human error, altitude was held constant and entry airspeed was decreased until the actual curve point was reached. It should also be noted that in this area, very little time is available to attempt to increase airspeed after the collective is lowered. In Area 2, after the 2-second delay to assimilate normal pilot reaction time, collective is lowered to decrease rotor decay. Then the flare is initiated. Let's take a look at the Area 2 test footage again. After the 2-second delay, to assimilate normal pilot reaction time, collective is lowered to decrease rotor decay. Then the flare is initiated. The final area on the velocity curve we will discuss is Area 3. Area 3's altitude is 75 feet and below. In Area 3, starting with the low hover point, no attempt to accelerate or regain rotor RPM can be made. With forward airspeed between 15 and 40 knots, a decelerating attitude can be assumed. Dependent on altitude, the collective can be lowered slightly to decrease RPM decay rate. In this area, increased ground roll should be expected. Let's view the test footage in Area 3 of the velocity curve. With low hover point, no attempt to accelerate or regain rotor RPM can be made. A decelerating attitude can be assumed with airspeed between 15 and 40 knots. Depending on altitude, the collective can be lowered slightly to decrease RPM decay rate. Ground roll should be expected. Again, let's view the test footage on the velocity curve in Area 3. Rotor RPM cannot be regained. Decelerating attitude can be assumed with airspeed 15 to 40 knots. Collective can be lowered slightly, and ground roll should be expected. Now, what does all of this mean to you as an individual aviator? By being exposed to some of the rudiments of engineering flight testing, you should have more appreciation for and reliance on the height velocity curve as a tool to help keep you out of serious trouble. Certainly, you are not expected to commit this curve to memory. However, the information should serve to stimulate your awareness of courses of action to follow should you experience an engine failure while conducting operational missions. You should not have to think about your immediate actions following an engine failure while operating at altitudes above 150 feet at an airspeed of below 60 knots. It should be an automatic reflex action to rapidly lower collective and attempt to gain airspeed. At altitudes between 40 and 100 feet, with airspeed below 40 knots, no attempt should be made to gain airspeed while lowering collective. A decelerating attitude would effectively decrease ground roll. Altitudes below 40 feet, with airspeed between 15 and 40 knots, the collective cannot be lowered to minimum without getting into more serious trouble. Slightly lowering collective and assuming a decelerating attitude will aid in decreasing RPM decay and ground roll. In summary, the information you have been exposed to should enable you to cope with whatever situation you may encounter during your career as an aviator. Absolute coverage of every possible emergency situation is not practical. However, having some knowledge of steps to take and using your own ingenuity, you should be able to cope with any emergency.